All right, let's try this again. Now that I think I actually have the mic connected. So like I was saying, we're switching everything over to labeling our outputs as loads. What are we trying to power? What are we trying to provide current and voltage for? We can go through different ways and we can solve these. Previously, we'd have to go through and solve the entire circuit again and again every time we change the load. Well, one of the methods we're going to talk about today, hopefully today, is the ways to solve these circuits without having to resolve the entire circuit. We solve it once up to a certain point, we can stick our load back in, and then we can calculate everything's going to be. But the idea behind this, we have some basics behind these guys. So we have maximum power transfer. And what this states, and when this occurs, this is when our load resistance is equal to the circuit resistance. And what this is saying is we're going to get the most amount of power out of our circuit that we can possibly get at this point of equilibrium. And so also what's saying, so what happens is as we build the circuit, we change things. If we decrease our load resistance, we're going to decrease the need for our circuit resistance to be as high. And in such doing, we're going to be changing the value of our curve for the power. So we have a higher circuit resistance, we're going to have a lower load resistance. It's going to result in a lower amount of power. When we become equal is when we're going to find this peak of the most power that gets transferred. That's one of the things you guys will be doing in the lab next week as well, is actually solving and going through using maximum power transfer. And you'll actually see this take effect. Okay, so the next thing we're going to talk about, so this is just the idea of this is where we have to get things equal. We have superposition. Superposition is a theorem, and it's a tool that we use for circuit analysis. So first thing, it's a circuit analysis tool. Where basically what we do is we go through and we look at each individual power supply in a circuit. We solve for it individually, and then when we're done, we combine the results together. So we're taking multiple power supplies and combining everything together to get one final answer across our load, across our different components, things like that. Oh my gosh. So, and in the end, what we're going to find out is depending on the orientation of the power supplies, one power supply is going to exert dominance over the other one. And things are going to follow its polarity more so than the others. So this is how we can put batteries in a circuit, and we can either put them in, so they look like they'd be series opposing, and we're going to find out what they actually do to our load, which is usually in the middle. We want to take some voltage from one, some voltage from the other, and combine it together in a different way. So that's one of the analysis methods we're going to be talking about is superposition. The next one we're going to talk about is Thevenin. Who here has heard of Thevenin's theorem before? Okay. What would you say it is, Zach? It sucks.
It's basically the way to find just a random 2 points to find the voltage between the two, right?
Yep. So the idea behind this is you could actually take out a component that you may not have much knowledge for to be able to solve for everything around it, and then when you get to the point, you can plug that back in. Also, you can use it to solve your circuit minus your load. So that way, as you change your load, you'll have to do one set of calculations instead of having to rerun the entire problem. And I'll show you guys some examples. Yes. And so Thevenin will get you most of the way there, but then you have to use Ohm's laws, Watt's laws, Kirchhoff's laws to finish out the problem. So Thevenin works great. You know, think of it like if you're having a party. Thevenin's the one that brings the beer pong game, but he decides to break the table and walk out before the party's finished, and then leaves your house trashed. So then Kirchhoff, they have to follow in behind and clean up the rest of the mess. So Thevenin will get you almost there, but it won't get you to the final answers for everything. We'll still have to rely on other parts, but it makes it a lot easier to get to the final picture in the end. So basically what this does is this reduces a circuit down to the most simplest form we could get. Usually one power supply and one resistor, then your load. So Thevenin reduces the circuit down to the most simplistic way we can to be able to solve for changing loads, or to be able to solve what is happening based on certain frequencies. As we'll start getting into with AC, we're going to see we'll use Thevenin to solve for frequency responses more so than for resistance responses, changing loads, things like that. We'll have the same circuit, just when we throw different signals and different frequencies, it's going to change everything. The next idea that we have is called terminal equivalency. Basically what this is if you can have multiple circuits, and as long as they have the same voltage and same current at the loads, they can be built 20 different ways, but they are equivalent because they're producing the same amount of voltage and current or giving the same amount of voltage and current to the load. So that's the idea, is we can have multiple ways to do it. As long as it meets our requirement, we don't care what they are or that they're different, just that they both are giving us the same thing. Yes. Or even, like you said, 2 plus 2 plus 2, or 2 to the third. You know, I know that's not quite as multiplying it, but the same idea is multiple ways to look at it to get to the same answer, as long as they're the same in the end. The next one we're going to talk about is a bridge circuit. Yeah. Tori can tell you all about bridge circuits. So basically what a bridge circuit is, it's a four-legged circuit that can accurately measure small changes in voltages and resistances. Okay? So for example, that's a bridge circuit. What the cool thing is with these guys is how these are used is you could actually use these. You set up, they have resistors that the more pressure you have on them, they're going to give you a different resistance, which is going to change voltage drops across these guys. You'll have these centered across like a pad if you're trying to determine if something's level or not. It's an electronic leveler. You have these sensors in each of these four corners. As this thing is going to sit, depending on how it sits, you'll see the level you'll get a voltage going from one side or the other. And you can have these set up to now with the feedback that comes off of this guy, so we could send this to a computer and it's going to determine if it gets a positive or negative voltage, what it needs to do with hydraulic arms underneath of it to shift everything to level out the platform to where you can attach things to it. You can also use it for scales. You would have those set up to where, as it would come on, the difference in the two sides could give you the voltage drops across the scales, or connected to part of the scale and not part of the scale. So as you get on the scale, it's going to weigh it down more compared to these guys. It's going to give you a voltage drop, which is then going to tell you how much things weigh. So there's lots of different applications, and that's why we're going to use this bridge, because it's in a lot of different circuits. It's really just a comparator, is the idea. Is it runs everything through, and then gives you a voltage that you can easily compare. The two types that we have balanced versus unbalanced. And basically the difference is our output voltage is either equal to 0 or it is not equal to 0. When it's all said and done, if the output, which is going to be right here across the center, if that output is balanced, it'll be 0 across the whole thing. If it's not, you're going to have a positive or a negative voltage. That's the other thing too, cool with this, is with a positive voltage coming in, we can also get a negative voltage coming out.
So which side is like more?
All right. So as far as terminology goes, that's what we're going to be covering for this first section. Like I said, there is a lot, but it's just further application of everything that we have been doing. So first thing I want to start in with is superposition. So basically the steps we have for superposition is we want to identify our voltage sources. We want to solve each supply individually by shorting out all the remaining sources. So when we do one, we're going to short everything else out. When we solve the next one, we'll short everything out according to that. Then after we've solved for all the sources and we've determined a final voltage, then we'll go back through and look at how each of these voltages are in relation to each other. What are their polarities? Are we adding to each other? Are we subtracting from each other? We'll be able to tell a lot of information by these and how our currents are going to flow and everything like that. So our circuit that we're going to start with is going to look like this. So now we're getting into multiple battery paths, multiple power sources. We got R1, R2, R3. This is V1, and this is V2. And our ground is right here. We have 200 ohms. We've got 150 ohms. And R3 is 330 ohms. V1 is 15 volts. And V2 is 6 volts. Thank you much.
Yes, sir.
So now what we're going to do is we're going to short out each of these supplies individually, solve for them one at a time, and we're going to do that and make sure we have everything connected and redraw our circuits as we go. So first thing we have to decide, where are our voltage sources? Do we have multiples? Yes. How many do we have? We just have 2. One of the things we could have later on is we could have a capacitor that is going to charge up at some point. Once that does, that's then going to act as a voltage source until it gets discharged. And usually we're going to build it in such a way that we're going to use that discharge for something to shift our waveforms around as we go. So we have two voltage sources that we have to supply, so we're going to have two redraws with this circuit. We're going to have one for our 15 volt and one for our 6 volt. So the first thing we want to look at is, what do these redraws look like? So I'm going to do this guy in purple, and I'll do this guy in green. So the first thing we're going to look for, or the first thing we're going to do, we're going to short out all the other supplies except for the one we're working on. So when we short it, what happens? No more 6 volts. We're taking it completely out of the equation. So now what we have is a circuit that looks like this. And am I allowed to bring that resistor around like that? As long as I maintain its connections. So one side of R2 is connected up to R1 and R3. The other connections, connected to the negative and R3 as well. So as long as we don't change the physical connections, we can shift things up, top and bottom, left, right, doesn't matter. So I have 15 volts. I've got my 200 ohms here. I've got my 330, and I have my 150. Now, is this something that we could solve for the voltage drops across this guy? Yes. So one of the first things we're going to solve for is our R total. Then I want to know my voltage drop across R1, my voltage drop across R2, my voltage drop across R3, and the polarities. The polarities are the easy part because they're going to follow what the supply is doing. So this side is going to charge R1 to a positive and negative that direction because of the voltage supply of how its polarity is. So which means this guy's going to have a positive to negative that way. So what is our formula to solving for R total? So we have R1 in series with R2 parallel with R3. So again, we can go through and we can solve for this equivalent resistance here by using our parallel laws. Product of the sum or reciprocals, either way it doesn't matter. Depending on what calculator you're using, it might be easier one way or the other. Because like when I'm using my TI-36, it's easier to do the product over the sum. Because the button for it is, I have to hit second to get into that option for the reciprocal. On my TI-83, I have a button right there on the side that's my reciprocal, so I can just plug that one in just as fast as I can anything else. So it also depends on what calculator you're using, which method you prefer. So in this case, I probably just use the product over the sum. So we take 330 multiplied by 150. We take that number divided by 330 plus 150. So the R total for this parallel branch is 330 times 150 over 330 plus 150. And what did you guys get? 103.125. Always remember, go out 3 decimal places. This is going to help keep everybody's answers a lot more accurate, a lot more aligned. So we have 103.125. So that means our total resistance is 200 plus this. So one of the things also when we're doing in parallel is what we've done is we've reduced this circuit. So now, when we have our parallel resistance, this is also what we're looking at. This is our R total for the parallel. This is R1. So now we've reduced our parallel network down to a simple series circuit. Our total is going to reduce that down farther, so we have one voltage supply, one resistor. So our total comes out to be 303.125. So now now that we have our total resistance, we need to be able to find the voltages across these guys. So now again, when we're looking at this, even in our simplistic view from here, come on. Maybe. I want to know what's the voltage drop here and what's the voltage drop here, because everything in parallel is going to have the same voltage drop based off of this resistance. So for VR1, I'm going to use voltage divider. So we take the 15 volts multiplied by our 200 ohms divided by this total resistance, which we just found. So 303.25. And that will give us that voltage drop. Yeah, 0.125, sorry. So what do we get for a voltage drop there?
9.896.
Okay. In this case, I would round it up because the next digit behind it's a 9. So that'll round it up to a 7. So VR2, VR3, these guys are going to be equal. So at this point, we know we have 9.897 volts here. I have 15 total. So that means this parallel branch has to be the 15 minus that 9.897. We could also run it through our voltage divider formula and get that same value by plugging in, instead of the 200, the 103.125. So what voltage do we get across VR2? Oops. Is how much?
5.103.
Questions or concerns about how to get that voltage? Okay. So now we have both of these. We have R2, R3, and R1. So the first thing we're going to do is we're going to take those values, we're going to go back to our original circuit, and we're going to put them on their resistors with their respective polarities. So in this case, we have a plus to minus, and a plus to minus. R1, we have 9.897 volts. And R3 and R2, we have 5.103 and 5.103. Now with that being solved, we have the circuit half solved. Because we still have this other power supply that we have to take into account. Everybody good up to this point? Okay. Good? Okay. So now we're going to take and we're going to remove this short. And we're going to short out supply 1 because now we're working on supply 2. So our circuit is going to look like this. We got R1, R3, R2, our voltage source, and we have to make sure we get it in the correct polarity. So this is 200, this guy's 330, This guy's our 150. And we have 6 volts. Yep, we're going to find the same values as before. Specifically, we need the voltage across R1, voltage across R2, voltage across R3. Now, the reason we're doing this is in the end, we want to find out what is the voltage and current going through R3. So this is going to be our load, we're going to say, for this guy. This is going to be some motor, some light, something that's going to do something. We want to find out what the voltage and the voltage and the current across this guy is. So what's the polarity of our voltages for this in this setup? So negative, positive. Negative, positive. So now we're going to go through the exact same steps that we did to solve for the voltages. In this case, we have it flipped now. So R1 and R3 are in parallel, with added R2 in series. So now we go through and solve. So what is the parallel portion of our circuit? How much resistance is there? So I've got one answer of 124.528. You good with that? And then our total, we're going to add 150 more to that. So our final voltage, or final resistance total, is 274.528 ohms. Now again, we want to solve for the voltages. So in this case, VR2 we can quickly find. So again, we're using voltage divider. So 6 volts divided by, or multiplied by the 150 ohms, and divided by this total resistance we found for up here. So 274.528. How much? 3.278 volts. R1 and R3 are going to be the same because they are in parallel. So again, we'll take the 6 volts and we'll subtract out this value, or we could go through and solve for this resistance parallel total that we have here in our formula. We would just replace this 150 with the 124. So we end up with 6 minus 3.278. And that gives us 2.722 volts. Everybody good with those values, at least getting the same ones as you're calculating them. Okay, so now we got to take these values. So we got 2.722, R2 is 3.278, and R3 is the 2.722. And again, we have, I don't remember those as we go. So the polarities. Come back up to our main drawing.